Hey everybody, in this video, we are going to introduce ourselves to a topic known as heat. But before we begin, let's go over a few concepts. The delta symbol, represented by an equilateral triangle, stands for change in. So if I say something like delta E, or the change in energy, I mean that I want the difference between the final energy and the initial energy, since if you subtract the final by the initial, you will get the change in energy. So let's now talk about another topic. The system is the part of the universe that we are focused on, while the surroundings is simply just everything else in the universe. So take, for example, a pot of water. If we want to heat a pot of water, now I don't know if I'm a very good drawer, but if you want to heat this pot of water, you're focusing on just the pot and the water, and that would be your system, while everything else around it, such as the air or maybe the ground, those would be considered the surroundings. Now, another concept you should understand is a state function. A state function is a property or trait that depends on the state of the system itself rather than the path it takes to get to that state. So, as an example, volume, mass, and energy are all state functions. And, for example, the mass of an iron bar will always be the same no matter what path you choose to make that iron bar. And because the path doesn't matter and it only depends on the iron bar itself, then mass is a state function. Now, there are two important things that are not state functions. Heat is not a state function because heat depends on how a process is done and does not depend on the state itself. For example, if you started with a pot of water, you have no idea how much heat you will put into it because the initial state, which is the pot of water, will not tell you how much heat you will add. In fact, the amount of heat you will add depends on the path you take, for example, if you decide to heat it more or less. And because of that, heat is not a state function. Another thing that is not a state function is work. The reason being is that the path determines how much work is put into something and not the state. So, for example, let's say you wanted to go out for an exercise, and let's just say that we want to find out how much work you are going to put into this exercise. Well, just by looking at you, we can't really tell how much work you are going to put into the exercise because the amount of work depends on the path you take. For example, you might do more or less depending on how you feel. So because work does not depend on the state, then work is not a state function. So now let's move on to a different topic, something known as heat. Heat, also written as Q, is the transfer of heat or thermal energy from the system to the surroundings or vice versa. So heat energy is a type of kinetic energy because heat is related to temperature, which is the measure of the average kinetic energy, if you remember from one of those videos in the past. So heat energy flows from objects at higher temperatures to objects at lower temperatures. Now this makes sense, since if you have a cup of boiling water, then obviously the boiling water will have the higher temperature, and the heat energy from the boiling water will want to travel into the air, and as a result, the cup of boiling water will cool down because it is releasing heat into the areas at a lower temperature, which is the surroundings. So this makes sense. Now, there are two things that we have to know. If heat energy flows into something, then Q is positive. This is known as an endothermic process. If heat flows out, then Q is negative. This is known as an exothermic process. Now let's take a look at this equation. The heat of the system is equal to the negative of the heat of the surroundings. Now, how does this make sense? Well, when a system gains a certain amount of energy, so it would be a positive amount of energy, then the surroundings would lose that same amount of heat. And this is due to the law of conservation of energy. So, to put it into perspective, if a cup of water, let's just draw this as a cup of water, gained 5 joules of heat energy, or positive 5 joules, then the surroundings, let me just put the surroundings as the S, must have lost 5 joules of heat energy, because all the energy went from the surroundings to the cup, and it wasn't destroyed nor created. Instead, it was just transferred. So the cup gains 5 joules of energy, while the surroundings loses 5 joules of heat energy. And this is essentially how this equation works. Since the Q of the system was plus 5 joules, so that means the Q of the surroundings must have been negative 5 joules. And you might be wondering, well, when do we know when the heat is negative or positive? Well, I just mentioned it right here. If heat flows in, then Q is positive. If heat flows out, then Q is negative. So the cup had some heat flow into it, so it was positive, while the surroundings lost some heat energy, so Q was negative in that case. Now let's continue our terminology journey. So the next thing we are going to learn is about the calorie, or CAL. 1 calorie is a form of energy, and it is equal to 4.184 joules. And 1 calorie is the amount of energy it takes to heat up 1 gram of pure water by 1 degrees Celsius. So, before we continue, note that increasing the temperature by 1 degree Celsius is the same thing as increasing the temperature by 1 Kelvin. Now you might be wondering, why is that? Well, this is because although degrees Celsius and Kelvin are 273.15 apart, if we increase degrees Celsius by 1, K will also increase by 1, and they will always be 273.15 apart. So that's a nice way of thinking about it. And in the end, increasing the T by 1 degree Celsius is the same thing as increasing the T by 1 Kelvin. So now I have one question for you. Is 4.184, which is equal to 1 calorie, is that an exact number or an approximation? Well, let's take a look and think about this. So 1 calorie is the exact amount of energy it takes to heat up 1 gram of pure water by 1 degree Celsius. But when we measure the amount of energy it takes to, heat up 1 gram of water, we are measuring it using tools. And because we are measuring it, and, we're measuring it in terms of joules to see how many joules fit into a calorie, which is the definition for the amount of energy it takes to heat up 1 gram of pure water by 1 degree Celsius, we are going to get some accuracy errors, because when we measure stuff, we are bound to not be perfectly accurate, but we can get as close as possible. So as a result, this is not an exact number, and this is actually rounded off. So this has 4 sig figs. Just keep a note of that. Alright, so now let's move on to a related topic. The amount of energy it takes to heat 1 gram of anything up by 1 degree Celsius is called the specific heat, denoted by lowercase c. So by definition, this must mean that the specific heat for pure water must be 1 calorie, or 4.184 joules, and we'll get into the units for specific heat later, but I wanted to point out this special equation over here, Q equals mcΔT. Now this is a very special equation because it tells us that if we multiply the specific heat C by the mass of the object in grams, and the change in temperature in degrees Celsius, then we will get the amount of heat that has been exchanged. Now, when you do this, make sure that all your units match up so that everything works. Now, before we continue, we have to think about what the units are for our specific heat. So, we know that heat is a form of energy exchange, so that must be in joules. And this is equal to grams, which is mass, times C times delta T, which is in degrees Celsius. Now, in order to find the units for specific heat, we move things around, and we get that C, our specific heat, has units that are defined as joules over grams times degrees Celsius. So this is the unit for specific heat, and it makes sense since it's saying that, like, how much energy does it take to heat up 1 gram by 1 degree Celsius? And remember that this is an invisible 1 there and an invisible 1 there. And this number over here might be 100 or, basically anything. So intuitively, the units make sense. So let's prove to ourselves why this equation works. So what if I said we have 10 grams of water, indicated by this question over here, and we heated it up by 2 Kelvin? How much heat would that equal to? Well, we have to think about this. Will Q be positive or negative? Well, if the water is gaining heat energy, then that means that it's endothermic, so Q must be positive. Now let's think about this. If we know that the specific heat is the amount of energy it takes to heat up 1 gram of water by 1 Kelvin or 1 degree Celsius, and since that's equal to, let's not use joules, let's use 1 calorie this time, then how much energy would it take to heat up 10 grams up by 2 Kelvin? Well, we can think of this logically. So if we need to heat up 10 grams instead of 1 gram up by 1 degree Celsius, then let's redraw that. So 10 grams up by 1 Kelvin or degree Celsius, then this would mean that we would need 10 times as much energy to heat up 10 times as much stuff, so that would be 10 calories. And if we want to heat it up by twice as much, not just 1 Kelvin, but 2 Kelvin, then that means that we need twice as much energy. So if we increase the temperature by twice as much as 1 Kelvin, then that would require twice as much energy, and thus we arrived at an answer that we need a total of 20 calories to heat up 10 grams of water up by 2 Kelvin. So this gave us an answer, and we could do it using the equation too. We can multiply the mass, 10 grams, times the specific heat, which is 4.184 joules per gram degree Celsius, times 2 degrees Celsius, and this would get us 83.7 joules, which is really close to 20 calories. So notice how the equation worked perfectly, and notice how the method we just used initially proves that all you do to get the amount of heat is just multiply the specific heat by the mass and the temperature change. So we just proved the equation, and now we are confident that it will work. So now let's move on to a very related topic. The amount of energy it takes to heat up anything by 1 degree Celsius is called the heat capacity, C. The equation corresponding to this would be Q equals capital C times delta T. Now, if you notice, this is basically a substitution of MC. And we use heat capacity because sometimes an object might not just be made of one thing with a constant specific heat that we could use. Instead, it might be made of many things, and perhaps some parts of the object might heat up more easily than other parts. Therefore, by simply finding the energy needed to heat up the object by 1 degree Celsius, then we know our heat capacity, capital C, and as a result, we can easily find the heat needed to heat up the object by 2 degrees Celsius, or maybe even 100 degrees Celsius or any other change in temperature. So heat capacity could be useful sometimes, but specific heat is also useful. So now let's move on to yet another related topic. This is a topic known as calorimetry. It is a method that we use to measure heat exchange. Now, there are two ways that we can do this. We can use a coffee cup calorimeter, and we do this in low budget settings, aka maybe in your classroom lab. But to be more professional, you would use a bomb calorimeter, which is heavily insulated and more accurate, since if you insulate the heat, then you'll get a more accurate answer when measuring the heat. So, how does this exactly work? Well, let's take an example. So, let's just say that we need to find the amount of heat put into 100 grams of water. So, let's just say that this is your cup, and let's just say we had a fire under it, and we want to find out how much heat was put into that 100 grams of water. Now, how do we do that? Well, here we see a thermometer, and this thermometer is cool because it can measure temperature for us. So, of course, we need to use the equation Q equals mcΔT. And we know that the C, the specific heat for water, is going to be 4.184 joules per grams times degrees Celsius. And we know that we have 100 grams of water. So when we start heating this up, all we need left in this equation is the change in temperature. So we might have an initial temperature of, let's just say, 25 degrees Celsius. And let's just say you heated it up so much that it's maybe 80 degrees Celsius. Now you have the change in temperature, delta T, right there. And doing the math, well, you kind of need a calculator for this unless you can do math in your head. So 100 times 4.184 times parenthesis 80 minus 25. And this will get us 2.3 times 10 to the 4. Oh, that's not a good looking for. 10 to the 4 joules. And I kept track of sig figs since this will give us 55. And 55 has 2 sig figs. And when you multiply that, your answer will have 2 sig figs. So, this is how calorimetry works. And this was a very simple example, but I think it did its job. So now that we are talking about heat, we can crawl into another topic yet again called enthalpy, which is indicated by a capital H. Enthalpy is essentially the internal energy of a system, such as the chemical energy, the kinetic energy, and the potential energy, and everything else, all combined to form the internal energy, which is everything. So, it is very hard to measure internal energy since you have to calculate all this stuff, and it's pretty hard because we don't have microscopes that are good enough to, see how fast things are moving, or maybe the potential energy, and, it's hard to measure internal energy. So, because of that, we measure the change in enthalpy instead of the enthalpy itself, since it's easier to measure. And the reason why it's easier to measure is because the change in enthalpy is equal to the change in heat. And we can measure heat using thermometers, so that's why it's easier to measure delta H. Now, before we continue, delta H applies to very specific circumstances. We usually use delta H to describe reactions that absorb or release energy in the form of heat. So let's take an example. Let's say that we're combusting some methane gas, and we want to find out the amount of heat that burning methane gas releases. So, by definition, the amount of energy released when burning 1 mole of methane gas would be the delta H of the reaction of burning methane gas. So, in other words, the delta H would be the amount of heat released when burning 1 mole of methane gas, which is our reaction. So to calculate delta H, there's a very simple equation. You simply take the amount of heat that was released or absorbed, but in this case it is released, and thus a negative number, since, when you burn methane, it releases heat, and you feel that heat. So the Q in this case would be negative, and that's the amount of heat released per 1 mole of reaction. Notice how in fractions, the top is always a number, while the bottom is always assumed to be 1. But sometimes you won't burn exactly 1 mole of methane gas. Sometimes you might burn maybe 0.5 moles of methane gas. So in this example, I want you to find the delta H of the reaction when 0.500 moles of methane is combusted and releases 100 joules of heat. And this is made up, so don't fact check me on this because I made up that number. So if 0.5 moles of methane combusts to release 100 joules of heat, that means that the heat must be negative 100 joules before the reaction. So the reaction releases 100 joules of heat, so, the reaction lost 100 joules, so it's a negative number. So how do we find delta H? Well, delta H is the energy that's released or absorbed when 1 mole of methane is burned. So this is for 0.5 moles. So to get 1 mole, we simply have to multiply this by 2. And we get that the delta H is negative 200 joules for every mole of methane burned. So you might be wondering, well, what does this have to do with anything? Well, the thing I just did, where I just doubled it, could be done very easily by just dividing the heat released by the number of moles of reaction, or in this case, the moles of methane burned. And in the end, negative 100 divided by 0.5 is negative 200. So I just proved that this equation works. So now that we talked about this, let's move on to our final topic. When delta H is negative, just as if Q is negative, then it's exothermic, or the reaction is exothermic. When the delta H of a reaction is positive, then the reaction is considered endothermic. Now, we have to talk about a few things about reactions because it's kind of different from when we were heating water, because now we are looking at the reaction as our system. So, when exothermic reactions release energy, or when the system loses or releases energy, then it would heat up the surroundings and increase the surrounding temperature. So that makes sense, since for an exothermic reaction like burning methane, it releases energy and it heats up the surroundings, which is why it feels hot whenever you put your hand close to a fire. Now, endothermic reactions are the complete opposite. They absorb energy. So if a reaction absorbs energy, that means it steals energy from the surroundings to, give itself energy. So it would steal heat from the surroundings and lower the surrounding temperature. So endothermic reactions cool down the surroundings, while exothermic reactions heat up the surroundings. So I talked about this example, and now let's talk about one final thing. Enthalpy, like energy, is a state function. Now, you might be wondering, why is energy a state function? Well, let's just take a very simple example. Let's take an ice cube. It would have a certain amount of internal energy, or enthalpy, H. And it doesn't matter if the ice cube was broken off from a bigger ice cube or made from water freezing, because in the end, you have an ice cube, and this ice cube has a certain amount of energy that did not depend on the path that it took to get there. So because of that, enthalpy is a state function. Now let's do a few questions regarding calorimetry, since we didn't really get to practice that. So aluminum has a specific heat of 0.900 joules per gram times Kelvin. If a 6.72 gram aluminum bar at 80 degrees Celsius is dropped into a cup of water at 25 degrees Celsius, and the final temperature of the cup of water and aluminum bar was 29 degrees Celsius, what is the mass of the water? Now, this is a really weird question at first because you're like, wait a second, it's not very straightforward. Well, it's not very straightforward, but we could figure this out. So we have a cup of water, and this cup of water has an unknown mass, but we know that it's at 25 degrees Celsius. And we have this bar, which is 6.72 grams, and it also is at 80 degrees Celsius. So when you drop it in, the final temperature of everything turns out to be around 29 degrees Celsius. So the question is asking, what is the mass of the water? Well, in order to do this question, we have to think about what gains heat and what loses heat. So since this is at the higher temperature and this is at the lower temperature, heat energy will flow from the aluminum bar to the water until they reach the same temperature. So let's see how this works. So if we remember, we have an equation that states that the Q of the system is equal to the negative of the Q of the surroundings. Now we have to choose which one will be our system and which one will be our surroundings. So let's just say that we are going to consider the aluminum bar as our system. So the Q of the bar, which will be the amount of heat that the aluminum bar loses, this will be equal to negative of the heat that is gained by the water. And this makes sense, since the heat that is lost by the bar is gained by the water, and that's why a negative sign is there, since opposite things are happening, but the quantity of heat is still the same. So using this, we can substitute Q for mcΔT. So the mass of the bar is going to be, well, let me check, 6.72 grams times the specific heat of aluminum, which is 0.900, times the change in temperature. So the change in temperature is equal to the final temperature minus the initial. So the final temperature is 29 degrees Celsius, and the initial temperature was 80 degrees Celsius. And this will be equal to negative of the mcΔT for water. So what is the mass of the water? Well, we don't know that. The specific heat of water is going to be 4.184, because we are doing this in joules. Since this was in joules per gram times degrees Celsius, this has to be in joules per gram times degrees Celsius. And the change in temperature would be the final temperature minus the initial, which was 25 degrees Celsius. Doing the math, we get this algebraic equation, and notice how I labeled the sig figs. This has two sig figs because 29 minus 80 is going to have 2 digits, and this has 1 sig fig since 29 minus 25 is 4, and that has 1 sig fig. So divide both sides by negative 16.74, so negative 308.4 divided by negative 16.74, and we get that the mass of the water is equal to 18.4 grams. But since we can only have 1 sig fig, we have to say that this is going to be 2 times 10 to the 1 grams of water, and this would be the answer. In the next video, we will go over enthalpy and a law known as Hess's law. So that's all for this video, and have a nice day.